All right, today we're going to learn how to make models of molecules. So we've learned how to draw the Lewis structures, but now we're going to learn how to put together the atoms in a model so that we can model what the molecule looks like in three-dimensional space. So I want you to please have your guided notes open, Chapter 5 guided notes, and be filling out this information. I've got a picture up here of a model of one of the most important proteins that there is in life. It's called hemoglobin. Hemoglobin is in every one of your red blood cells, and what it does is it binds oxygen. When you breathe in, the oxygen will find this hemoglobin molecule in the middle of your red blood cells, and then it takes that oxygen to all the cells of your body. But this is a model of what hemoglobin looks like. So it's a representation. Is it exact? I don't know, because proteins, are they microscopic? Yeah, they are. But we can create models for stuff that are so small we can't even see. And that's what we're going to be doing today. We'll show you how to build a water molecule. You can't see it with your eyes, but we can create a model to kind of represent that. Anyway, so here we go. Models are attempts to explain how nature operates on the microscopic level based on our experiences in the macroscopic world. So even though we can't see these molecules, we can build a model and try to represent what they look like in the microscopic world. Here's a famous example. Models can be physical, like Watson and Crick. Did you guys remember these guys from biology? Oh, yeah. They were the first scientists to build a model of DNA. And so this is the double helix they're looking at here. And they built this model which really did help them figure out how DNA replicated, how it was transcribed, and eventually they won the Nobel Prize for it. Models can be mathematical. It might just be an equation. Okay, it can be mathematical. It can be theoretical or philosophical. Models can be represented in a number of different ways. A model does not equal reality. Okay, we don't know for sure what it is, but a model is our best guess. From all the evidence that we have built, it's our best guess of what is happening at that microscopic level. Models are oversimplifications. A lot of times they're way too simplified, and therefore a lot of times they're wrong. Models become more complicated as we learn more about them, and as the idea kind of grows. Models can become very complex. We must understand the underlying assumption in a model so that we don't misuse it. We're going to study models of molecules today. It's kind of difficult to kind of show you guys models of molecules on a two-dimensional board. This board goes left to right and up and down, but it doesn't go into the board and straight out toward you guys, does it? So since it's impossible to show 3D models on paper, chemists use the following notation to show a three-dimensional model. So here is a model for CH4. So let me put that here. If we were going to model this molecule, well, I could write its structure. Its Lewis structure ends up looking like this. But in reality, that's not what it looks like at all. Because in reality, it looks like this. But how can I show you that on a two-dimensional board? I can't. So what chemists will do is use a little bit of notation. If you see this dashed line right here, that means this hydrogen is going straight back into the board. When you see a wedge, like this hydrogen has a wedge, that means this hydrogen is coming straight out towards you. So in reality, these two are on plane with the board. This one's behind the board and this one's coming out in front of the board. And so if I hold up my model like this, it would look like that. Okay, this one would have the wedge. This one is have the dashed lines going back into the board. And these two are on plane with the board. So it's very difficult to represent three-dimensional molecules on the board. So anyway, that's how we'll do it. So a dashed line means what, guys? Going back into the board, and this wedge is coming out of the board. Okay. All right. Okay, this model that we're going to talk about today is called the Vesper Model. It stands for something. This is an acronym. VSEPR is an acronym that means valence shell electron pair repulsion. So this is the V, the S is shell, the E is electron, the P is pair, and R is repulsion. So valence shell electron pair repulsion. This Vesper model helps us predict the shape of molecules and what shape they're going to take. The idea behind Vesper is that the shape of the molecule is determined by minimizing electron repulsions. Guys, if this was an electron right here and I put another one right here, and I was to let them go, which way would they want to move? Do electrons like each other? They don't. Like charges repel each other. And that's the whole main idea behind Vesper model, is we try to minimize the electron repulsion. Electrons will move so they are the farthest apart from each other that they can possibly get. And based on that, we can come up with a model of what these molecules will look like. Okay, so Vesper theory predicts that molecular shape of a bonded molecule. Electrons around the central atom arrange themselves as far apart from each other as possible. These electrons or these bonds will move as far apart from each other as possible. Unshared pairs, which, what do we call unshared pairs, guys? Lone pairs. On the central atom will repel the most. So if there's just two dots, you know those lone pairs? These guys repel the most. So only look at what is connected to the central atom. We're only going to be concerned about what's connected to the central atom. Okay? So, molecular shapes that we're going to study. Number one, they're called linear. What does linear mean, guys? You had math? Yeah, it's a straight line. So the bond angles are 180 degrees. Linear means it's a straight line. Bond angles are 180 degrees. The second one we're going to study is called trigonal planar. Trigonal planar. And the bond angles are 120 degrees. Trigonal planar. I'll show you what that looks like later. The third one is tetrahedral. Tetrahedral, the bond angles are 109.5 degrees. Between each bond, you could measure that angle, and it would measure 109.5. Then there's number 4, trigonal pyramidal. In trigonal pyramidal, the bond angles are less than 109.5 degrees. And then finally, the last one that we will study is called bent. In a bent molecule, the bond angles are less than 109.5. So less than 109.5. Okay, so let's quickly run over those again. So we got linear, straight line, trigonal planar, tetrahedral, trigonal pyramidal, and bent. Okay. We're going to go through each one of these in a lot more detail individually here. So let's start with this one. Linear. When you have a linear molecule, you have two atoms attached to the central atom. You have two atoms attached to the central atom. You're supposed to write that there. And you have 0 unshared pairs, or 0 lone pairs. So if you do the Lewis structure and it's got two atoms attached to the central atom and 0 lone pairs, what's its shape going to be? Linear. Okay, the bond angles in a linear molecule is 180 degrees. That's a straight line. Here's an example. Carbon dioxide. Look, it's a linear molecule. Everything lies along this straight line right here. What's our central atom in CO2? Which one goes in the middle? carbon. So this is our carbon atom. Our oxygens are here. This is an oxygen and this is an oxygen. And you'll notice that you have two atoms attached to the central atom. There's one, there's two. No lone pairs. So we know that it's linear. Okay, let's go to the next one, trigonal planar. Trigonal planar has three atoms attached to the central atom. So in this case, three atoms will be attached to the central atom and zero lone pairs. Bond angles are 120 degrees, like a triangle. It kind of forms like this triangular shape. Bond angles are 120. Here's an example. If this was boron right here, and these three were fluorine, you have zero lone pairs. And so if you've got three atoms attached to the central atom and no lone pairs, then it's trigonal planar. Okay, tetrahedral. Tetrahedral has four atoms attached to the central atom and no lone pairs. Zero lone pairs. Bond angles are about 109.5. An example of this is CH4. So this is my carbon atom. It's a central atom. These are hydrogens here. If I asked you the shape or the molecular geometry of CH4, you would say tetrahedral. Okay, so four atoms attached to the central atom and zero lone pairs. All right. The next one is called trigonal pyramidal. Trigonal pyramidal has three atoms attached to the central atom. What other shape has three atoms attached to the central atom? Trigonal planar. Well, here's the difference. Trigonal pyramidal has one lone pair. Trigonal planar had zero. So if it's got three atoms attached to the central atom and one lone pair, we know it's trigonal pyramidal. Bond angles are about 107. Here's an example of a trigonal pyramidal molecule, NH3. So this is my nitrogen. This is hydrogen. This would be a hydrogen, and this one's a hydrogen. But hydrogen would have a lone pair right here. So if it's got a lone pair and three atoms attached to it, it's trigonal pyramidal. And it kind of looks like a pyramid. So here's an example of trigonal pyramidal. If you see it on the counter here, it does look kind of like a pyramid. The two lone pairs that would sit up top here are repelling these other electrons in these bonds, and it's pushing it down, so it kind of looks like a pyramid. So that's where the name comes from. Okay, the last structure, the last geometry is bent. In a bent molecule, there are two atoms attached to the central atom. And it has two lone pairs. So two atoms attached to the central atom, and it has two lone pairs. Bond angles 104.5. An example is water. Water has a bent geometry. So if this was water over here, our oxygen would be this atom. This would be a hydrogen. This would be a hydrogen. But it's got two lone pairs. So there's a lone pair here, and there's a lone pair here. These lone pairs are repelling the electrons in these covalent bonds here and pushing them down. And so that's what makes it bent. So here's an example of water's geometry. The two lone pairs that sit up here bend down these covalent bonds and make it bent. So I'm going to put water on the test. Don't draw it linear. A lot of students like to make it linear. It's not. Water is a bent molecule. Water's bent. Okay, so steps to solving Vesper questions. First, you've got to draw the Lewis structure. We know how to do that. We learned how to do that last time. Identify how many atoms and lone pair electrons are attached to the central atom. Look at your molecular geometry sheet that paper that I gave you, that blue paper, and pick the correct shape for your molecule. Here's the paper that I just gave you. Okay, if it's linear, it's got one atom attached to the central atom, or it has a structure similar to these. Tetrahedral. How many atoms attached to the central atom, guys? So here's my central atom is X. How many atoms attached to it? 4. This was drawn with the wedge or the dashed line notation. Trigonal Pyramidal. How many atoms attached to it? 3, but it doesn't have a lone pair. Yeah, so 3 atoms and one lone pair is trigonal pyramidal. Bent, how many atoms attached to it? 2. And how many lone pairs? 2 lone pairs this time. And finally, trigonal planar, how many atoms attached to the central atom? 3. Any lone pairs? No. So all we have to do is draw the Lewis structure, look at this paper right here, and we got it. So I'm going to ask that if you're watching the video, please have this paper, the geometries, out so that when we do these problems, you can look at it and have it easily accessible. Okay, practice problem number 44. It says to draw the Lewis structure and determine the correct geometry around each atom for the following molecule. CO2. What's step 1? We got to draw the what? Lewis structure. Well, how many valence does carbon have? 4. How many valence does oxygen have? 6. But how many do I have? 2. So what's 4 plus 12? Isn't that 16 valence electrons? Which one's going to go in the middle, guys? Carbon. So let's draw carbon's dot structure. 1, 2, 3, 4. Now, if I'm going to make it symmetrical with my outside atoms, if I put an oxygen here, where should I put my other one? On the other side. Okay, remember that molecules prefer to be symmetrical, which means a mirror image. How many dots, though, does oxygen bring? 6. So I'm going to draw 6. 1, 2, 3, 4, 5. Can I put 3 dots here? No, so I'm going to skip that part and put 1 down here. 6. Let's draw 6 on this one. 1, 2, 3, 4, 5, and 6. Okay, now we're not done with our Lewis structure yet. We've got to make sure that they're obeying the octet rule. We've got to make sure that we have 16 valence electrons. How many dots do I have, guys? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I do have all electrons accounted for, but is oxygen obeying the octet rule? Nope. Is carbon? No. Oxygen looks like it has 7, this carbon only has 6, and this oxygen has 7. So if they're not obeying the octet rule, what do, guys? We share more, introduce more covalent bonds. So I'm going to take this single electron here and this single electron, and we're going to share and make another covalent bond between this carbon and oxygen. Okay, so let's count the valence around oxygen now. 1, 2, 3, 4, 5, 6, 7, 8. Would it be happy then? Sure, it'd be stable. It has an octet. Same thing with this oxygen. We're going to move this electron, and they're going to share between them. So that when I redraw this, let's redraw it. Now there's 2 shared pairs between the carbon and oxygens. Do I still need my lone pairs out here? Yes, you do. Okay, am I done? No. So now we need lines representing the covalent bonds, these bonds between shared atoms. So it's going to look like this when you're all done. Okay, so that's my Lewis structure. How can we be sure? Let's count the valence. 2, 4, 6, 8, 10, 12, 14, 16. Is carbon obeying the octet rule? 2, 4, 6, 8. Is oxygen? 2, 4, 6, 8. Everything's good. So That's our Lewis structure. Now what I want you to do is get that blue paper, the geometry paper, and let's look at our central atom. Which one is our central atom? Carbon. Where do you see that structure on this paper? That would be linear. Notice how it's a straight line, guys? So with respect to the carbon, here's what you're going to put. Carbon, it's linear. Okay? So CO2 is a linear molecule. Everything goes along a straight line. Let's try another one. Practice problem 45. I want you guys to try this one on your own. Draw its Lewis structure, pick up the geometry sheet, and tell me which one it is. Out of those 5 shapes that we just studied, which one will it be? If you're watching the video, please try it on your own first. Then, so hit pause and then hit play once you're done. Okay, so let's see how you did with this one. Carbon has 4 valence. Hydrogen has 1, but I've got 4 hydrogen atoms. If we add up our valence electrons, that's 8, right guys? Right. Carbon's going to go in the middle, so I'm going to draw its dot structure. Has 4 valence electrons, so I'm going to draw 4 dots. Guys, where do you think these 4 hydrogen are going to go?
All around it.
Yeah, it has to surround it, right? It brings 1 electron to share. So are all of these going to be covalent bonds? Yeah, so I need lines on all of them. So this molecule is really going to look like this. Okay. But in reality, is it a flat molecule like it showed here on this 2-dimensional board? No. So let's get its geometry. With respect to the carbon, now I'm just looking at the central atom here. How many atoms are attached to carbon here? There's 4 atoms attached to it. Any lone pairs? No lone pairs. Which shape on your paper has 4 atoms attached to it and no lone pairs? It's tetrahedral, right?
Tetrahedral.
So this molecule is tetrahedral. Okay. With respect to the carbon. Hey, now, that's with respect to the carbon. What if I ask you this, guys? With respect to the hydrogen, what is it? So, with respect to the hydrogen, what is it? So now I'm looking at this hydrogen. How many bonds does it have to it?
4.
The hydrogen?
No. Just
1. Whenever it has just 1 bond, what is it? Linear.
So, whoa.
Okay? So the molecule is tetrahedral because carbon's our central atom. But if I asked you with respect to the hydrogen, I hope that you would be able to tell me that the hydrogen bond is linear. There. Okay. All right. 46. Again, let's try this one. I think you guys would be pretty good at drawing the Lewis structures now. So draw the Lewis structure, then grab your geometry paper and tell me what shape it is. Right, Hayden? Okay, if you're watching the video, please hit pause, try it first, then hit play. Okay, so let's see how you guys did with this molecule. It's called ammonia. Very famous molecule. Nitrogen has 5 valence. Hydrogen has 1, but I got 3. So if you add them together, isn't that 8 valence electrons? Okay, does hydrogen ever go in the middle? No. So I'm going to draw nitrogen's dot structure. How many dots? 5, because it has 5 valence. Okay. Where do you think these 3 hydrogens are going to go?
On the sides and bottom.
Yeah, it can't go on top. That one already has 2 dots. So let's put them where we can. So there's 1, 2, and 3. Okay, now out of these electrons, which ones are covalent bonds? Shared between 2 atoms? That's a covalent bond, this is a covalent bond, and this one. What do we call these 2 electrons? A lone pair. So this is the first time we see a lone pair. So let's see how it looks. So this molecule is going to look like this. Okay. Everyone's obeying the octet rule, and we've got our 8 valence electrons. 2, 4, 6, 8. Okay, so we've accounted for it. Now, if you look at your paper, I want you to tell me the geometry of this molecule. What's the central atom? The nitrogen. Count how many atoms are attached to it. Well, there's 1, 2, 3. And we have one lone pair. So 3 atoms attached to it and a lone pair. Look at your paper. Which one is that? That's trigonal pyramidal. So with respect to the nitrogen, the shape of this molecule is trigonal pyramidal. Okay, how many of you guys got that right? Very good. With respect to the hydrogen, what would it be? Hydrogen, it would be linear. Just has one bond on the hydrogen. So, but overall, the shape is trigonal pyramidal. Here's what a trigonal pyramidal molecule looks like. This lone pair right here is really repelling the electrons in these covalent bonds and pushing them down. And so if you look at it, it kind of does look like a pyramid. So trigonal pyramidal. All right, practice problem 47, the most famous molecule. I want you to draw it and make sure you get it correct. This is a very important one. Okay. Draw the Lewis structure and tell me its geometry. All right, let's see how you did with water here. Hydrogen has 1 valence, but I've got 2 hydrogen atoms, so I'm going to times it by 2. Let's add that to the valence of oxygen. Oxygen has 6 valence. So what's 2 plus 6, guys? Isn't that 8 valence electrons we have to account for? Does hydrogen ever, is it ever your central atom? Nope. So we're going to draw oxygen and draw its dot structure. How many dots? 1, 2, 3, 4, 5, and 6. Where do you think these 2 hydrogens are going to go? Well, the only place they can is here on the left where there's 1 opening here. Remember, hydrogen brings 1 electron to share. And on the bottom here, hydrogen brings 1 electron to share. Now, I've got to draw lines for my covalent bonds. Where are my covalent bonds? Between the 2 atoms that are sharing electrons, right? So it's going to look like this. Do I still need my lone pairs on the oxygen? Yes. Okay. So this is the correct Lewis structure for water. Now, take out your geometry paper that I gave you. Let's look at the atoms that are attached to the central atom. Our central atom is oxygen. How many atoms does it have attached to it? How many atoms here, though? 2. And how many lone pairs? So 2 atoms attached and 2 lone pairs. If you look up its shape, what is it, Brandon?
Bent.
Thank you. With respect to this molecule, it is bent. Guys, please remember that water is not linear. It is bent. Water is bent. The most famous molecule ever. It's bent. With respect to the hydrogen, though, what is it? Linear. Hydrogen always has 1 bond, so it's going to be linear. Okay, so that's a bent molecule. All right, there's one more that we haven't looked at. Let's do this one. Okay?
This
one's kind of difficult. I will give you that. Try it on your own first, though. If you're watching the video, please hit pause and try it. Okay, let's see how you did. Carbon, how many valence? Guys, stay with me. Let's go fast. 4. How many valence from the hydrogen? 1, but how many do I have? 2. How many valence from the oxygen? 6. If we add all of these together, what's 4 plus 2 plus 6? That's equal to 12 valence. We've got to account for all of them when we're done with our Lewis structure. Which atom always goes in the middle? Carbon does. So I'm going to draw its dot structure. How many dots around it? 4 dots. It has 4 valence. Okay, now we're going to try and make it symmetrical. So where am I going to put these 2 hydrogens? Maybe if I put one here, where should I put my other one? The opposite side. Okay, now it doesn't really matter where you put the oxygen, but I like to put it on top, so I'm going to put mine up here. Could have I put it down here? Yeah, it wouldn't have changed anything. Okay, so it doesn't matter. How many dots? 6. 1, 2, 3, 4, 5, and 6. Okay, now let's count my dots and make sure I need to have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got them all accounted for, but are they obeying the octet rule? No, the hydrogens are, because they got 2, and that's all they want. But the carbon, 1, 2, 3, 4, 5, 6, 7. The oxygen, 1, 2, 3, 4, 5, 6, 7. So if they're not obeying the octet rule, what do we do, Tandon?
You move not the lone pairs, but the two that aren't the lone pairs.
So single electrons?
Yeah, that's right.
Okay. And you move them where? So here's a single electron.
To the middle.
Good. You move them between the two atoms that are not obeying the octet rule. Okay. So let's redraw this so that it looks a little cleaner. Okay, so we got this going on. And now instead of one shared pair between the carbon and the oxygen, we have two. Do I still need these lone pairs right here?
Yep.
Yes. Now, am I done? No, because I need to locate and put a line in for my covalent bonds. So when I redraw this for my covalent bonds, it's going to look like this. Okay, and this is the correct Lewis structure for this molecule. If you look at carbon, now it's obeying the octet rule. It's got 2, 4, 6, 8. The oxygen has 2, 4, 6, 8. And the hydrogens just want 2. And let's make sure we have 12 electrons still, 12 valence. So we got 2, 4, 6, 8, 10, 12. So we are good. Now, here's where a lot of you are going to make a mistake. Which atom are we really trying to figure out here? The central atom. Which one was my central atom? Carbon. Okay? So with respect to the carbon, how many atoms does it have attached to it? Well, it's got a hydrogen, it's got an oxygen, and a hydrogen. So how many is that? That's 3. There's 1, 2, and 3. Does it have any lone pairs? No. So which one has 3 atoms attached to it and no lone pairs on this geometry paper? That's trigonal planar. So with respect to that central atom, it's trigonal planar. Okay, very good. Guys, with respect to the hydrogen, what would it be? Linear. With respect to the oxygen, what would it be?
I don't know.
It's just got one atom attached to it. It would have to be linear as well. So trigonal planar with respect to the carbon. Okay, before I quit the video, I want you to review the 5 shapes we just learned, the geometries. What are they? Linear.
Trigonal planar.
Trigonal planar.
Trigonal.
Trigonal pyramidal. Bent.
Tetrahedral.
And tetrahedral. I want you to just remember, water is what, guys? H2O is bent. So whenever you draw water from now on, make sure that it's bent. Because that's going to be important going forward. All right. Good news, guys. We're learning so much. We are learning so much. Yeah, this is good news. I want you to turn to your student workbook. There's a worksheet called Vesper Worksheet. Turn there now and complete the Vesper Worksheet. And hopefully this video helped you.